let's now look at the asymptotes of the Hugoniot. So we could show that the asymptotes, so the way we actually try to find out the asymptotes of this Hugoniot curve is to substitute that 1 over rho infinity goes to infinity, and then find out what's the value of p infinity for 1 over rho infinity going to infinity to get this asymptote. For you to get this asymptote, you now substitute p infinity is equal to infinity in the Hugoniot relation, and then try to find out what's the value of 1 over rho infinity, right? So can be shown to be, that means you show as in, like, you can do this as an exercise, and it can be like a typical quiz question or an exam problem. 1 over rho infinity equals 1 over rho naught times gamma minus 1 divided by gamma plus 1, and p infinity equals minus p naught minus p naught gamma minus 1 divided by gamma plus 1. Now notice that gamma is the ratio of specific heats which is greater than 1, so let's suppose it's about 1.25 or something like that. So this is going to be like point something divided by 2 point something. So gamma minus 1 divided by gamma plus 1 is going to be always less than 1, and so 1 over rho infinity is always going to be less than 1 over rho naught, and therefore your asymptote is going to be to the left of the origin. Alright. And similarly gamma minus 1 divided by gamma plus 1 again is less than 1, and it's going to be a fraction of p naught. That means it is going to be less than the value at the origin, but with a negative sign, right? So it's now going to the other side, and obviously that's not possible, right? So so this is less than 0, not possible, not physically possible, right? So the practical range of p infinity is 0 less than p infinity less than infinity. It can go up to infinity, that's possible. So what is the range of rho infinity? That's now going to span between where the Hugoniot intersects. So let's suppose that's how it's intersecting. So that goes asymptotically to the lower bound there, which is impossible, but p infinity equal to 0 is about where you can go up to 1 over rho infinity. You can't go below this because p infinity cannot become negative, right? Therefore this is like your uppermost value of 1 over rho infinity. So you can try to find that out by plugging in p infinity equal to 0 in the Rankine-Hugoniot relation, right? And then try to solve for 1 over rho infinity and get an expression. The lowest value is when p infinity becomes infinity, so that's corresponding to this particular value itself, of the asymptote, right? So the range of 1 over rho infinity is 1 over rho naught gamma minus 1 divided by gamma plus 1, which is what we have for the asymptote we saw just a little earlier, and you're not going to really touch it because it's an asymptote, and therefore you're not going to really touch p infinity equals infinity, so you're always less than that, and so 1 over rho infinity is always greater than this, not really greater than or equal to, but you can go up to greater than or equal to what's now called 2q divided by p naught plus gamma minus 1 divided by gamma plus 1, I'm sorry, this is gamma plus 1 divided by gamma minus 1 1 over rho naught. Now notice that this is actually dependent on Q. That means if your Q is larger, the Hugoniot shifts to the right and above and top, and therefore the point where it intersects the P infinity equal to 0 axis shifts further and further out, right. So sure enough, as you increase your Q, this term is going to linearly increase, right. So this is a range. Now what we also noticed was notice that the first quadrant of the Hugoniot plot is not possible because the Rayleigh line has a negative slope. So this divides the Hugoniot into two parts, the upper branch and the lower branch. So you can now begin to see what those limits are for these each of these branches. So the Hugoniot curve is divided into two branches. The lower and the upper, right. So along the upper branch, the ranges are P naught plus gamma minus 1 Q rho naught less than or equal to P infinity less than infinity. That's going from here all the way up to infinity, right. So what we are actually locating, this is P naught plus gamma minus 1 Q rho naught. So as Q increases, this curve is going to go up. So the point where this intersection happens is going to go up, right. So P infinity, then the lowest value of P infinity will keep moving up as Q increases. So this can obviously be obtained by plugging in 1 over rho infinity is equal to 1 over rho naught in your Rankine-Hugoniot relation, right. So each of these expressions can actually be derived by plugging different things in the Rankine-Hugoniot relation. Okay. The question is, for what do you need to plug what is something that you have to think about and use your mind, and you can get these expressions, but these are like little problems that you can face in your exams. Okay. This is like a fertile ground for asking lots of little questions, right. Just to basically test your algebraic skills, not really combustion skills. Okay, and then this is as far as the P infinity is concerned, and of course the lowest value of rho naught that you can rho infinity, I'm sorry, 1 over rho infinity that you can get is the asymptote, and the highest value is 1 over rho naught itself. That's very easy for you to figure out, right. So again we can write 1 over rho naught gamma minus 1 divided by gamma plus 1 less than 1 over rho infinity less than or equal to 1 over rho naught. That's the range for the one over rho infinity along the upper branch. Along the lower branch, the ranges are Again, if you are now looking at P infinity, it's going to go from here, that's the highest value is P naught, and the lowest value is this, right, which is 0. Therefore, so it's going to go from 0 less than or equal to P infinity less than or equal to P naught. Okay, and you now look at the lower branch. It starts from here, so the lowest value of 1 over rho infinity is corresponding to this value, which is obtained by plugging P infinity equal to P naught, right. So if you now plug P infinity equal to P naught in the Rankine-Hugoniot relation, you should now get an expression that we should now be able to see readily, depends on Q linearly. So 1 over rho naught plus gamma minus 1 divided by gamma Q divided by P naught less than or equal to 1 over rho infinity less than or equal to, that's the other end where the P infinity becomes 0. This is something that we have already figured out, that's this value, right. So that's 2Q divided by P naught plus 1 over rho naught gamma plus 1 divided by gamma minus 1. Good. So these are just algebraic expressions that you can get for the different limits for the upper branch and the lower branch separately. Okay. Now as we noticed, we can clearly see from here that the upper branch corresponds to a compression wave that actually decelerates the flow, and therefore we call it a detonation wave. The lower branch is a expansion wave which accelerates the flow, and so we call it a deflagration wave. Okay, these are things that we noticed. The next thing that we wanted to point out was we wanted to actually find out what is the speed at which the detonation waves travel and what is the speed at which the deflagration waves travel. So the way we wanted to actually look at it is, what is the speed of the lowest or the slowest detonation wave, and what's the speed of the fastest deflagration wave. And obviously we can see that they are sort of poles apart. Okay, so that is the slowest detonation wave is still going to be much faster than the fastest deflagration wave. So let's see what they tell us. Okay, and these are corresponding to the Chapman-Jouguet detonation and deflagration waves. So what we want to actually look for is what's the incoming Mach number. Incoming Mach number at the CJ points, on both branches. Alright, so this is what we should be looking at now. So how do you locate the two CJ points, right? Obviously you look at any point that is like a solution of both intersection of the Rayleigh line and the Hugoniot is by solving them together, right. So the Rayleigh line has its P infinity and 1 over rho infinity showing up, and the Hugoniot curve has its 1 over P infinity and 1 over rho infinity showing up. So that is to say that if you now solve for P infinity and 1 over rho infinity together with these two equations, you now should get a pair of P infinity and 1 over rho infinity that corresponds to coordinates that satisfy both the equations, and that means that that's a point where both of them intersect, right. But in addition to that, at the CJ points we also have to match the slopes, because the Rayleigh line is tangential to the Hugoniot curve, right. So let us first try to get the end states at the CJ points. End states as in the infinity conditions. Right. So at the Cj points, the slopes of the Rayleigh line and the Hugoniot curve match. So that means we have to first of all find out what is the slope at any point on the Hugoniot curve and then match it to the slope of the Rayleigh line, so that the slope of the Hugoniot curve is dp infinity d over d1 over rho infinity. This is something that you can actually obtain by simply differentiating the Hugoniot curve with respect to 1 over rho infinity, right. So wherever you are getting a p infinity, you try to now differentiate that with respect to 1 over rho infinity, right. So then you get a p infinity minus p naught times, sorry, minus 2 gamma over gamma minus 1 times p infinity divided by 2 gamma divided by gamma minus 1 over rho infinity minus 1 over rho naught plus 1 over rho infinity. That is the slope expression that you get for any point on the Hugoniot curve. This is actually the slope at any point, okay. We are still not saying that this is at the Cj points. At the Cj points, it turns out that the slope should now be equal to the Rayleigh slope, right. So slope of the Rayleigh line what's the slope of the Rayleigh line? The Rayleigh line is a straight line, okay, and so long as we don't want to use the m dot squared expression, that's like a no, yeah, because we want to deal with only the thermodynamic properties. So for a straight line it is just p infinity minus p naught divided by 1 over rho infinity minus 1 over rho naught, that's it, right. So is p infinity minus p naught divided by 1 over rho infinity minus 1 over rho naught. So equating the two, we can get so we can get like a, for example, p infinity equal to p naught rho naught divided by rho infinity times gamma plus 1 rho naught divided by rho infinity minus gamma. So here what we have done is we have eliminated, or we have now written an expression for p infinity in terms of the other three, p naught, rho naught and rho infinity, okay. In fact we always should be looking for rho infinity to show up as 1 over rho infinity. So sure enough this is 1 over rho infinity here, this is 1 over rho infinity here, and we are also getting it as rho naught over rho infinity everywhere, right, here as well as here, okay. So essentially that means we should now be in a position to eliminate p infinity in favor of rho infinity, or rather 1 over rho infinity. Or if you want to do it the other way, you can now try to get an expression for 1 over rho infinity in terms of p infinity, p naught and 1 over rho naught, okay. So or 1 over rho infinity equal to 1 over rho naught times gamma p infinity divided by p naught times 1 plus gamma, or rather you used to writing gamma plus 1 p infinity divided by p naught minus 1, okay. So you can use either of these expressions. So these are both at Cj points. both these expressions are valid at Cj points. Okay, it doesn't really solve much. We have not really got the coordinates yet, because here P infinity depends on rho infinity. So what is it meant by saying getting the coordinates? We should now be able to write P infinity only as a function of P naught, rho naught and Q. Okay, and 1 over rho infinity we should be able to write in terms of P naught, 1 over rho naught and Q. But this is the mixed thing. We just can eliminate, because we can write explicit expressions for P naught at the P infinity at the Cj point and 1 over rho infinity at the Cj point in terms of the others, which will still contain the other infinity term. P infinity will contain 1 over rho infinity term, and 1 over rho infinity will contain P infinity. Okay, so there are these other things. So we still haven't solved for the coordinates, which is what we are now going to do next. So substitute either of these, right, in the Hugoniot, or should strictly speaking say Rankine-Hugoniot, to give Rankine his due. Relation, so that what happens is if you now write P infinity in terms of 1 over rho infinity in the Rankine-Hugoniot, you don't have P infinity at all in that expression. You will now have an expression that's only on 1 over rho infinity, which means you can now write what is 1 over rho infinity in terms of everything else, right? So but unfortunately you're now going to get a quadratic, okay, in either of these, but it's actually fortunate, if physically fortunate, mathematically a bit unfortunate. You have to deal with quadratic equation, but it's physically fortunate because this says only Cj. Matching the slope simply means that we are just working at any Cj point. It could be the upper Cj point or the lower Cj point. Either of these Cj points, the Rayleigh line is tangential to the Hugoniot. It's not distinguishing between those two, right? And we are therefore looking for two solutions to 1 over rho infinity and P infinity at the Cj points, one of which will correspond to the upper Cj, the other one corresponding to the lower Cj point. So here, so substitute either of these expressions in the Rankine-Hugoniot relation to get a quadratic in either P infinity or 1 over rho infinity, and solve the quadratic. So if you now solve the quadratic, you get P infinity plus or minus equal to P naught plus gamma minus 1 Q rho naught times 1 plus or minus 1 plus 2 gamma P naught divided by Q rho naught gamma squared minus 1 the whole to the half. Okay, now let's call this small a, the expression for P infinity plus or minus 1, and 1 over rho infinity plus or minus equal to 1 over rho naught plus gamma minus 1 divided by gamma Q divided by P naught times 1 minus or plus 1 plus 2 gamma P naught divided by Q rho naught gamma squared minus 1. So that's kind of like the same as what we had before, to the half, right? Okay, so here what happens is when you now say plus or minus, this plus goes with the plus here, this minus goes with the minus here, right? But here this plus or minus is such that this plus goes with the minus there and this minus goes with the plus here, right? So when you say, basically say plus or minus, you simply mean upper Cj or lower Cj. That means we are expecting that for the upper Cj your P infinity should always be greater than P naught, therefore P infinity plus will correspond to P naught plus this, okay. Lower Cj is going to be having a P infinity less than P naught, therefore P infinity minus should be equal to P naught plus this minus with a negative sign. That means you are going to have a less than. And similarly here 1 over rho infinity, you are now going to have 1 over rho infinity, that is for the upper Cj you need to have a 1 over rho infinity that is less, right. Therefore you need to have a negative sign over there, and for the deflagration Cj point, the LCj point 1 over rho infinity is greater, therefore you need to have a plus. So the lower sign will always correspond to a LCj, upper sign corresponds to a UCj, right. So upper sign corresponds to UCj, lower sign corresponds to LCj. So we now got the coordinates, great. So of course we need to call this B, right. Good. I mean in fact getting this particular thing, you know, substitute those two expressions in the Hugoniot curve expression, the Rankine-Hugoniot relation, and get the quadratic and solve the quadratic to get these. This is actually done for each of those separately, right. You will sweat a little bit, it's going to take like some amount of time doing all this stuff, okay. But it could be a bit boring, but you wade through the mathematics to see how the terms basically get grouped the way they are, okay, and then it's going to be pretty instructive for us because of what we are going to do next. Now what we want to do is what do we want to do? Okay, what we want to do, we want to now look at what's the incoming Mach number. Why do you want to look at the incoming Mach number? Because we want to know how fast the Cj detonation wave and the Cj deflagration wave are going to travel, right. Now keep in mind how fast is the wave going to travel is an information that's contained in u naught, okay, because in a wave fixed coordinate system you are going to have the reactance travel to the wave at that speed, and that information is now in our scheme of things embedded in m dot, because m dot is the one that's containing rho naught u naught as well as rho infinity u infinity. So it serves purposes of carrying the flow information on either side of the wave, right. And since we are actually looking at the incoming Mach number, we should be focusing on u naught. That means we are looking at m dot through which we will try to look for rho naught u naught, and m dot doesn't show up in the Hugoniot curve, it's showing up only in the Rayleigh line, right. So we should now go back to the Rayleigh line and say, it's sort of like saying, look at what we have done. We have substituted the slope matched information into the Hugoniot curve to get this, but can I now look at how the Rayleigh line is going to be like if I plug these coordinate points in the Rayleigh line and then get an m dot information through that? You see what I am saying, okay. So we have really not used the Rayleigh line information except to note that that is the slope, but that's just a thermodynamic that is just the slope written in terms of thermodynamic variables. We have not brought in the fact that this is equal to minus m dot squared, right. So that's what we want to do now. So we want to now notice that the slope that we had used for the Rayleigh line is actually equal to minus m dot squared, and then get to the flow information. So using A and B okay, so simply just go back and write what it is, P infinity minus P naught divided by 1 over rho infinity minus 1 over rho dot equals minus m dot squared. Right, we can now get our m dot squared divided by P naught rho naught plus or minus equal to gamma plus q rho naught divided by P naught times gamma squared minus 1 times 1 plus or minus 2 gamma P naught divided by q rho naught gamma squared minus 1 the whole to the half. Okay, note that m dot equals rho naught u naught, and the Mach number m naught is going to be written as u naught divided by a naught, which is nothing but u naught divided by square root of gamma p naught divided by rho naught. If you now notice that m dot is nothing but rho naught u naught, so now you write your u naught as m dot divided by rho naught. Okay, so you now plug that over here, you will now get your this is nothing but square root of m dot squared divided by gamma p naught rho naught. So we had m dot squared by p naught rho naught, all right. Okay, and then we now are looking for m dot squared by gamma p naught rho naught under square root is your Mach number, or m naught squared is now going to be m dot squared divided by gamma p naught rho naught. That's I mean, this is something that is basic. It's nothing particular about whatever we are doing. It is like just putting these things together, right? So from here we should now be able to write m naught plus or minus as 1 plus q rho naught divided by p naught gamma squared minus 1 divided by 2 gamma the whole to the half plus or minus q rho naught divided by p naught gamma squared minus 1 by 2 gamma the whole to the half. So it's sort of like falling into some sort of a pattern there, and this is what we were looking for. So because it's going to say something to us, so at the CJ points. Okay, so what we can see from here is when q goes to 0, right. So when q goes to 0, this goes to 0, this goes to 0, right. So you just get m naught plus or minus 1 is equal to 1, all right. So when q goes to 0, we get m naught plus or minus 1 equal to 1. We can say goes to 1, right. And we will also see that m infinity plus or minus 1 at CJ points equal to 1. That's something that we will do next. Okay, so what that simply means is nothing is happening when you don't have any heat release. It's as if like you had a wave that is going at the sonic speed, okay, and not really changing anything about your gases. The gases are basically non-reactive gases, that means you're not having any heat release, and that's as if like you had gases go at sonic speed and nothing happened to it. Okay, that's not a very interesting situation for us. But let's now look at the other possibility. What we are really interested in is when you have non-zero Q. Now how would you actually look for a non-zero Q in the Rayleigh line? As I said, when you now have a Q greater than 0, as Q increases you now have this Rayleigh line push up like that, away and away from the origin of the Hugoniot, right? And as you now go up to Q tending to infinity, let's say you now had Q going to infinity, right? This curve is going to actually go and hit the Rayleigh line. This Cj point is get pushed to infinity, and this Cj point is going to get pushed to infinity here. All right, and what you're going to now see is either your 1 over rho your P infinity is going to go to infinity, or your 1 over rho infinity is going to go to infinity. The P naught is going to go to 0 over here. Your 1 over rho your P infinity is going to go to 0 here, and your 1 over rho infinity is going to go to the asymptote. This is how it's going to push, right? So if you now look at the limit then, so as we strictly speaking don't have to look at Q going to infinity itself, what really matters for us is in this expression Q rho naught divided by P naught goes to infinity. Then if you now use the positive sign for the UCJ, that's a detonation wave, then both these terms add up together towards each other, and then m naught plus goes to infinity, right? So m naught plus goes to infinity, but m naught minus goes to a 0. These two terms essentially subtract from each other. Of course 1 is like a small number when compared to these infinities that we are talking about, so m naught minus goes to 0, right? So what this means is what you're then saying is then for the Chapman-Jouguet detonation wave, keep in mind when Q is equal to 0, m naught plus or minus both of them are going to be equal to 1. That's a lower limit as far as the heat is concerned, right? So for the Chapman-Jouguet detonation wave we have m naught plus go from 1 to infinity, right? And for the Chapman-Jouguet deflagration wave, we have 0 less than m naught minus less than 1, you see. So these are the limits that we are talking about, therefore this is how it's going to pan, and what that means is the m naught is not really going to overlap between these two, okay. So this is going to go only up to 1, that's going to go only above 1, okay. So that means a detonation wave propagates at supersonic speeds, and a deflagration wave propagates at subsonic speeds. Well, let's not just jump to that conclusion yet. There is just one more step that we have already talked about. The reason why and then I want to bring that in to generalize this quite well. The reason why we were actually looking at m naught plus or minus at Cj points is, keep in mind the Cj detonation is the slowest of all the detonation waves, and the Cj deflagration is the slowest of all deflagration waves, right. So if you now have a Cj wave that is supersonic, right, that's a Cj detonation wave that is supersonic, all other detonations are going to be supersonic because this is the slowest. And if a Cj deflagration wave is going to be subsonic, then all deflagrations are going to be subsonic, right. So this implies that, right, all detonation waves propagate at supersonic speeds and all deflagration waves propagate at subsonic speeds. Right. So that's exactly what we were expecting or thinking will happen. We also thought about a few things, which is what happens downstream over here. So if this wave is going to travel at supersonic speeds for detonation waves and compresses the gas, the reactants, as they now become products, they are compressed, they also decelerate. So the question is, do they decelerate down to what? Okay, so the answer there is they could decelerate down all the way down to subsonic conditions, or they could get decelerated to supersonic conditions that are still slower than the incoming supersonic speed. This is typically what you're expecting when you're now looking for a detonation wave that is not a Cj detonation. So if you now have any detonation, right, you can now have solution here and here, and this is something that's going to correspond to a very high pressure and very low density, sorry, very high density as well, very low 1 over density. Therefore we are expecting it to get a lot compressed and therefore a lot decelerated, so it can get down to subsonic speeds over here, and on this side it's not going to be that much compressed, therefore it's not that much decelerated. So you could expect that this is not decelerated down to subsonic speeds, but it's supersonic, yet less than slower than the incoming supersonic speed, and therefore we need to anticipate that at the Cj point the outgoing wave is actually going at sonic conditions, right. So this is what we need to anticipate, and let's see if that's going to work out. So downstream Mach numbers at the Cj points right. So what we then get is we had this expression that we had this expression by matching the slopes of the Rayleigh and the Hugoniot curves, right, for either the P infinity or the 1 over rho infinity, which we substituted earlier in the Hugoniot curve to get the coordinates of the Cj points, alright, and from there we now plugged that value in the Rayleigh to get the m dot, and from there we now went to the upstream Mach number. But we can do something different here. We have at the Cj points P infinity equal to P naught divided by gamma plus 1 minus gamma rho infinity divided by rho naught, or 1 over rho infinity equal to 1 over rho naught times gamma divided by gamma plus 1 minus P naught divided by P infinity. I think this is slightly different from what I just said a minute ago, but it's possible for you to derive this by dividing the numerator and the denominator appropriately by let's say P infinity and 1 over rho infinity and so on. So let's suppose that you have these. What you did was you actually plugged this into the Hugoniot curve expression and got the quadratics and solved them to get the coordinates for the LCJ and the UCJ. But if you can now go back and actually plug these in the Rayleigh line itself, right. So substitute either of these in the Rayleigh line, equation, and note that this time we are interested in noting that m dot is not rho naught u naught, because we are interested in the downstream conditions. So m dot is actually rho infinity u infinity. So note that m dot equals rho infinity u infinity, right. You should get, right. So to get, simply get m dot squared equals gamma P infinity rho infinity. Now this is not very different from what we had over here. You see, you got, as I told you, we could have written this as m infinity is equal to u infinity divided by a infinity equals u infinity divided by square root of gamma P infinity rho infinity, and then notice that plug this back in this here, and then you can get m dot square divided by gamma P infinity rho infinity. If you got that, and then by substituting this expression you also got this, that simply means that m infinity is equal to 1, right. So this is simply going to mean that m infinity plus or minus equal to 1. Now in a mathematical sense this is not surprising, because we plugged this expression in a Rayleigh line which is essentially linear, right. That's just a straight line, therefore we aren't expecting any quadratics, right. So if you don't have a quadratic, then we can't get two solutions, we should get only one solution, and that's only one solution. Okay, we strictly speaking shouldn't even write a plus or minus, we are not even at the stage of distinguishing between plus and minus, both of them are the same. So that means we are basically looking for the same answer for the downstream Mach number in either of these points, right. That is to say the downstream Mach number at both Cj points, right, at both Cj points is unity. This implies the Cj detonation decelerates supersonic reactant flow to sonic product flow, and Cj deflagration accelerates subsonic reactant flow to sonic product flow. I'm just going to abbreviate there because it's pretty obvious now. If that is going to be the case, so the next step that we do is to then say that if you got a strong detonation, then strong detonation means supersonic reactant flow becomes subsonic product flow, right. Cj detonation is what we just saw, supersonic reactant flow becomes sonic product flow, and weak detonation becomes supersonic reactant flow, all right, but still supersonic product flow with m infinity less than m naught. Okay, you still have a deceleration. Weak deflagration means subsonic reactant flow becomes subsonic reactant flow still becomes subsonic product flow with m infinity greater than m naught, still less than 1, right. So we should strictly speaking say with 1 less than m infinity less than m naught, the previous case. Here we should say with m naught less than m infinity less than 1, right, is what we should say. Cj deflagration, we saw subsonic reactant flow become sonic reactant flow, sorry, product flow, and strong deflagration, subsonic product reactant flow becomes supersonic product flow, which is impossible because it violates second law, which we have not explicitly considered mathematically, and we will not do that just to except to state that this is not going to be possible physically. We'll stop here for the day, and we will try to wrap up this one on Monday.